Today's topic is pressurization. So, pressurization systems. This will be important if you're on your commercial check ride. I was asked about pressurization systems on my commercial pilot check ride. You don't need to get super into detail. I'm going to go over the very, very basics of it and not going into a lot of detail. But this is just enough to what you need to know for your commercial pilot check ride. So, we're going to look at, you know, what pressurization systems are, the reasons for having them, the advantages. Many modern general aviation aircraft are designed to operate at high altitudes. You've got your Cirrus jet that has that pressurized cabin, and there's also additional requirements for operating with pressurized systems and at these higher altitudes. Um, Basically, aircraft are flown at higher altitudes for two main reasons. One, there's less fuel consumption for a given airspeed at a high altitude because the aircraft is more efficient in that thinner air. And two, bad weather and turbulence may be avoided. So let's define high altitude now. FAR 6131 states that high altitude is operations above 25,000 feet. However, a lot of high altitude effects can be felt well below 25,000 feet. We can feel hypoxia well below 25,000 feet. So let's talk about some physiological hazards. The human body above 12,000 feet MSL has decreased oxygen saturation, and that will affect your performance, running you into hypoxia. Hypoxia is simply a lack of oxygen, and our time of useful consciousness decreases exponentially when we get higher than 10,000 feet. So we can see at 20,000 feet, if we enter a depressurization system, our time of useful consciousness is 30 plus minutes. Then up 10,000 feet, that shrinks down to 1 to 2 minutes. Up another 10,000 feet, 15 to 20 seconds. And time of useful consciousness is defined as being the time from when you're exposed to that decompression to the time where you can make a corrective action. So we can see that increase in altitude exponentially diminishes our time of useful consciousness. So some symptoms of hypoxia will be cyanosis, headache, poor reaction time, impaired judgment. Euphoria is one of the main indicators of hypoxia, drowsiness, lightheadedness, all of these symptoms here. The thing is, different people have different symptoms, and throughout the course of your life, your symptoms will change. You can do things like going into a hyperbaric chamber and really seeing what your specific hypoxia symptoms are so that you can then better self-diagnose. Because a lot of pilots get hypoxic, become euphoric, have that general state of well-being, and then all of a sudden are unable to self-diagnose that hypoxia. Now, our treatment being to lower altitude and then utilizing supplemental oxygen if available. So with hypoxia, our vision tends to deteriorate with altitude, especially at night. When we're flying at night, we're using our rods as the primary source for those cells being the source of our vision, and rods are more susceptible to oxygen deprivation. So the FAA's recommendation at night is to fly anytime you're above 5,000 feet to utilize supplemental oxygen. Hyperventilation can occur as an early adaptive mechanism to hypoxia. If you feel like you're becoming hypoxic and you start to hyperventilate, and then that anxiety and stress really exaggerates that hyperventilation, it can make that even worse. And trapped gas. Expanding gas in body cavities can lead to pain in the abdomen, ears, and sinus. And then nitrogen absorption or decompression sickness. So we'll see this most commonly in people who scuba dive. Once they're under that high pressure while they're scuba diving, nitrogen gets built up in their muscles and in their tissues. And then if they fly immediately after, that nitrogen hasn't had enough time to rid itself from the tissue and can create these bubbles in the body. So the symptoms being just severe pain in the affected areas. If you run into decompression sickness, don't put pressure or be touching the affected area that's painful. If you have a passenger, make an emergency descent and land as soon as possible. And again, after scuba diving, provide the body with sufficient time to rid of excess nitrogen. All right, so we kind of talked about the physiological hazards. Now we'll get into what pressurization is. So pressurization, the benefits being, um, in general aviation aircraft, the higher end of cruising altitudes will be maybe between 6,000 and 8,000 feet. But most pressurized cabins are designed for aircraft operating anywhere from 25,000 to 50,000 feet. And again, if we're able to operate at those altitudes, there's less fuel consumption for a given airspeed because the aircraft's more efficient in that thinner air, and we can avoid bad weather and turbulence by staying above it. Additionally, a pressurized cabin gives us the benefits of not having to wear oxygen masks. There's a lower risk for decompression sickness. There's less noise and vibration. You can better control the temperature inside the cabin and cockpit. Better air ventilation. And so there's a lot of benefits to pressurized aircraft. So it's kind of the basic overview is our cabin is this sealed unit that's able to contain air under a high pressure when compared to the outside air. So we've got a big area of high pressure inside the aircraft, and then outside is area of low pressure. So the cabin is constantly being expanded or pushed upon, if you will. And there's a structural limit, depending on the aircraft, called the differential pressure, which is the difference between the high pressure inside the cabin and low pressure outside the cabin. And different aircraft, different airframes will have different limitations and different differential pressure limitations that they need to stay within. So for basic operation, fuselage in our cabin is a sealed unit. Compressed air is brought into the fuselage, and an outflow valve maintains the pressure. So the way that compressed air is brought into the fuselage is through the compressor of either a jet engine or turbocharger. So if we have, I'll take this for example, it doesn't have exactly the outlet that goes to the cabin, but basically we have this compressor that compresses the air, and then that sends it to the engine. So it sends that higher density air to the engines, makes it more efficient. Then that exhaust gas is rerouted, and it goes through a turbine. That turbine connected to a shaft is what spins that compressor to really compress that air. Additionally, it's not illustrated on here, but say there was another, outlet from the compressor. That heated compressed air, either from a turbocharger or from a jet engine, is forced into the cabin through these like air outlets. But before it can go into the cabin, this air is piping hot. So it goes through a heat exchange or a heat shroud where that air is cooled and then forced into the cabin. And then what regulates the pressure in the cabin is this outflow valve. So the air pressure is regulated by this outflow valve that maintains the set pressure in the cabin through a controlled leak. So it's only letting a certain amount of air escape. It's usually set at about the aircraft's maximum differential. Remember that there's a differential pressure between the high pressure inside the cabin and the low pressure on the outside. We additionally have this safety / dump valve, and this will act as a backup in the case the outflow valve fails, gets clogged or whatnot. Usually set slightly above the maximum differential. So in the case of a depressurization or outflow valve failure, that air can be dumped and also act as a backup to the outflow valve to really make sure that we have that cabin pressure set through that controlled leak, having a backup for that essentially. So there's a couple instruments that are additional to the pilots in the cockpit. We have our cabin pressure and control system and instruments. So provide pressure regulation, pressure relief, vacuum relief, and cabin altitude selection. So choosing what our cabin altitude is. It's controlled by our cabin pressure regulator, outflow valve, and safety valve. So we have our cabin differential pressure, which is this instrument right here. Again, cabin maximum differential pressure is set at a certain point. Remember, the airframe can only undergo so much pressure for the limitations of that specific aircraft. The cabin altimeter, so the height, the altimeter within the cabin, And so it looks like it's also a part of this pressure indicator here, and on this guy here. So this cabin pressure is at about 5,000, almost 6,000 feet here. And then our cabin rate of climb and descent. So this is the rate of climb of just the specific cabin pressure for when you make a change to that cabin pressure, the rate in which that change is happening. Now there's different types of decompression. Decompression is the inability of the pressurization system to maintain its design pressure differential. So there's two categories, really three main categories of decompression. There's explosive decompression. So the pressure changes faster than the lungs can decompress. So that change happens in less than 0.5 seconds. Then there is rapid decompression. So our lungs are able to decompress faster than the aircraft. Explosive decompression can lead to injury in the lungs. That air is forced out of you because that pressure is changing faster than our lungs can decompress. Indications: a slow decompression may be insidious, and so this is that third category of a decompression, which is that gradual decompression, which is arguably the most dangerous because it's, again, insidious and can only be indicated by the instruments. And again, remember, hypoxia is something where you get that euphoria feeling and it's hard to self-diagnose. So that gradual slow decompression can become a larger hazard than the explosive and rapid decompression. And a faster decompression, like an explosive or rapid, will include loud noise, may feel dazed, cabin suddenly filled with dust, fog, flying debris, air will rush out. People can actually be sucked out of the aircraft if that differential is large enough. The dangers, primarily for this slow decompression, is hypoxia. All of a sudden, the higher we are in altitude, right, the less time we have for our time of useful consciousness. And so, if you're in an airliner, that's when that Dixie cup will fall from the ceiling, and you put that cup first on yourself, and then on someone next to you if you're next to a child or something, and decompression sickness. So the actions are to get on supplemental oxygen immediately, and then as a pilot, emergency descent to a safe altitude. All right, and that's about it. That's a really simple overview of pressurization systems. That's really all you need to know for a commercial check ride. I was asked about it on mine. I gave maybe about a tenth of the information I talked about in here, and the examiner was satisfied. I basically just explained why aircraft would want to fly higher, and so they do that with pressurization systems, and saying that, well, there's some benefits to it, less noise, less risk of decompression sickness, oxygen masks don't need to be worn, better control of temperature and better air ventilation, and then explaining how there's just compressed air from the compressor in our engine that gets put through a heat exchange, is forced into the cabin. An outflow valve sets the pressure in the cabin through a controlled leak, and then there's a backup safety valve. That's really all you need to know. If you could just spit whatever I just said in the last minute out, you're good to go on the check ride pretty much. All right, well, that's about it for that one.